So for the horizontal and vertical stretching and shrinking, we start from some generic known function f of x and talk about a constant positive factor c. If c is greater than 1 and it is on the outside, we have cf of x, then our function will be stretched vertically by that factor c. If we have c on the inside, f of cx, then it is shrunk horizontally by that factor c. And then if c is a fractional or decimal amount between 0 and 1, then cf shrinks by c vertically, and f of cx stretches by a factor of c horizontally. As usual, like all of this notation here, it actually is a little bit confusing, especially considering you can think about a vertical stretch as being very similar to a horizontal shrink, really, but we'll see an example or two and we'll have a better sense of how this actually works. So for our first example, we want to use the graph of the absolute value function to graph g of x equals 2 times the absolute value of x. So here, remember, because we have that 2 on the outside, we're in this first case up here, which means that we are stretching vertically by a factor of 2, or making the graph taller and thinner, as it were. But let's get one more example here so we can see this in a different way. For our next example, what we want to do is use the graph of f of x equals x squared to graph g of x equals 1/2 x quantity squared. And the reason why you say that these things kind of work in the same way is because, while thinking in that last example, you could actually bring in the 2 into the absolute value and you'd have exactly the same sort of thing there with the horizontal shrink. And then with something like that 1/2, you could take the square in there and note that in this case, stretching horizontally by that factor of 1/2 would be the same as, well, shrinking vertically by a factor of 1/4. It works out that way. Making these things a little bit distinct does make it a bit more confusing than it needs to be, but sometimes it's quicker to be able to recognize that. In this case, that factor of 1/2 is going to make our graph a little bit wider, and something wider is the same as making it less tall in this context. We end up with a picture like this. And we're just about done here. We've seen a little bit of everything, but before we finish up, let's take one quick example here that puts together a few of these different things that we've seen. So we want to use the graph of f of x equals x squared to obtain j of x equals 2 times the quantity x minus 1 squared plus 3. Okay, so here we're going to have to think first in terms of what our most basic piece is, it being, because of the square, something quadratic flavored. And then from there we want to think about this in terms of the order of operations almost, where on the most inside thing done to this function is the subtraction of 1. So we're moving that graph 1 unit to the right. Then we're multiplying the whole thing by 2, so we're stretching it vertically by a factor of 2, or we're shrinking it horizontally by a similar factor, depending on how we want to see that. And then from there, the last thing we do is we take all those pieces, all that movement so far, and just pull it up 3 by that vertical shift from the plus 3 to get a picture of that. This is a pretty straightforward section for the most part. There's not a whole lot to be done here except to just see some of these basic pictures. So from here, we're going to look at some, let's say, slightly more involved things, where we're going to be talking about how we can pull functions together using algebra and compositions.